Okay, so I'm gonna begin. So the first problem that from the homework that you guys needed help with was trig number 3. It says find the least positive integer n such that this left-hand side is equal to 1 over sine of n degrees. And so essentially the key idea here is to notice that every term is of the form 1 over sine n times sine of n plus 1. And then you can note that sine of 1 can be written as sine of n plus 1 minus n. And using the sine A minus B expansion formula, you can write that as sine n plus 1 cosine n minus sine n cosine n plus 1. And so you can rewrite this fraction as 1 over sine 1 times sine n plus 1 minus n, which we over sine n plus 1. So these values are the same. And so by writing it like this, then you can further write it as, and this is 1 degrees by the way, and you can further write this as what we wrote here. So you can write it as sine n plus 1 cosine n minus sine n cosine n plus 1 over sine n plus 1. So essentially what we did is you just note that you have this fraction and then you can multiply it by any unit. Like basically we're just multiplying it by 1 or 1 over 1. Because that's what this reduces to. So we're basically just multiplying it by sine 1 degrees over sine 1 degrees because that's what this is. And these two are just equal. And when you expand that, just we get this like nice fraction right here essentially. And so by rewriting it, we can like re-express this fraction. So that becomes 1 over sine 1 degrees times, and we can split this thing into two different fractions. So if you divide this part by the denominator, then the sine n plus 1s will cancel out, and you'll get cosine n over sine n. And if you divide this part by the denominator, then you would get minus, and the sine n's would cancel out, so you would get minus cosine n plus 1 over sine n plus 1. And then so what you would end up getting is 1 over sine 1 degrees times cotangent of n degrees minus cotangent of n plus 1 degrees. And then now what you can notice here is, I mean, obviously at first sight, like something you would think about when you see something like this is like, oh, telescoping probably has something to do with it. But now that we made this reduction, we can see how telescoping would actually apply. And that's kind of the motivation for rewriting this expression like this as well, because now it's a difference. And obviously things are gonna cancel out if you if you write this as a sum repeatedly. So the actual question starts at 45 and ends at 133 for this value, which is n. So then, and um, that means that we can basically write the summation as k is equal to 23 to 67 of 1 over sine 2k minus 1 times sine 2k, because it starts with an odd number, and then the next one is an even number, which is 1 more than that. And we start from 45 again. And then 67, 2 times 67 minus 1 is 133. So this is a summation describing the original sum that they give us. And then we can rewrite this as 1 over sine 1 times cotangent of 45 minus cotangent of 46 plus cotangent of 47, and then so on till cotangent of 133 minus cotangent of 134 as per this new expression we got and for each of the terms. And so then we see that since we can use the fact that cotangent of 180 minus x is equal to negative cotangent of x, and this is due to the fact that cosine would be cosine of x is equal to negative cosine 180 minus x, and sine of x is equal to sine of 180 minus x. And since cotangent is cosine over sine, then we get that it has a similar behavior as cosine essentially. And so we can see that basically almost all of this stuff will cancel out except for cotangent 45 and cotangent 90. And this would end up being 1 over sine 1 times cotangent 45 minus cotangent 90. And that's equal to 1 minus 0 over sine 1, which is 1 over sine 1 degrees. And thus, it wants us to express the sum in terms of 1 over some sine n degrees. And so here we find that n is equal to 1. And since it's an AIME problem, you'd write as 0, 0, 1. And so the reason also, if you're wondering how all this stuff basically cancels out, it is just that, as you can see, cotangent of 46 and cotangent of 134 can be paired up. And then same goes for cotangent 47 and cotangent 133, and so on, and so everything starting from here onwards in the sum would be paired up with another number, and they another cotangent, and they cancel out, except for cotangent 90, because 180 minus 90 is just 90, so there's nothing to pair up this cotangent with. So cotangent 90 and cotangent 45 are the only two terms in this sum that would not be able to be paired up. And so it ends up giving you a final answer of n is equal to 1. If you guys have any questions, then put them in the chat, and then otherwise tell me if I can move on to the next homework problem that you guys need help with. Andrew, to your question, yeah, those two cases are exclusive. Essentially, for complex 1, you can split the you can just deduce the whole question to two cases where the magnitude of the complex number is 0 or 1. And if it's 0, you should get a single solution, which is a comma b is 0 comma 0. And then if the magnitude is 1, then you should get 2003 different solutions. In fact, those are the 2003 complex roots of unity. And so then when you sum it, you should get 2004. That's essentially how the solution should look like. But you can text in the chat if you want me to actually like walk through it. Otherwise, just text in the chat if I can go to complex 2 and show how to do that. Okay, if no one has any questions, then I'm gonna move on to the second problem that Andrew said you needed help with from the homework. So the second problem that he needed help with was complex 2, and this is a complex number z and w satisfied z to the 13th is equal to w, w to the 11th is equal to z, and then they write this like generic expression for the imaginary part of z, and we need to find that expression. So what we can do first is we can just substitute the first equation into the second. So the first equation gives us that z to the 13th is equal to like w, and the second equation is w to the 11th is equal to z. So we can substitute the value of w in that's given in the first equation into the second equation, and that would give us that z to the 143rd is equal to z. And then thus, we know that z is not equal to 0 because it says that the imaginary part of z is this expression, and m and n are relatively prime positive integers, so thus it has some non-zero imaginary part. So we know for certainty that z is not equal to 0, thus we can divide by z on both sides of this equation. That's an important part if we're dividing by like z or like x. Let's say if we replace x in this equation, something like that, then we have to verify that that variable cannot be equal to 0. So z is obviously not equal to 0, and thus we can divide by z on both sides, and we get z to the power of 142 is equal to 1. So z has to be a 142nd root of unity, and we can write that out. And then we know that so for any root of unity, the imaginary part of z is gonna be of the form sine 2k pi over 142. And rather the 142nd roots of unity are cis 2k pi over 142. And so we can simplify this to sine of k pi over 71. And k would range from the values 0 to 70, or rather 1 to 70. And we note that 71 is prime, and k has to be less than 71. And so by the conditions of the problem, the denominator in the argument of this value is always going to be 71, because all the values from 1 to 70 don't share any prime factors with 71, obviously. So regardless of what the value of k is, the denominator is always going to be 71. So we have that our final answer is just 71. Because like m and 71 essentially will always be relatively prime if m is some value from 1 to 70. So the idea here is just noting that z has to be a 142nd root of unity, and then noticing that you can write it as this, however you can simplify that fraction. And that is necessary because it says that m and n are relatively prime positive integers. You want to simplify as much as possible. And then you note that k has to be any value from 1 to 70, and all those values are relatively prime to 71. And thus n will always be 71, regardless of what root we choose. And there are many different roots we can choose. So text in the chat if you have any questions, or if I can move on to our number theory lecture and those problems, or if there's another homework problem that you need help with. Okay. And there's a request for me to do algebra trig 1 from the homework, so I'll do that as well. And again, if you guys have any more homework problems, just put them in now, and I'll get to them after this question. So for this question, we need to find all the positive solutions for this equation. First of all, the first thing we can do is we can rewrite cosine 4x as 2 cosine squared 2x minus 1. And now we have like a lot of cosine 2x's in the equation, so clever substitution would be to write cosine 2x as some a. And so then you can write this as 2 times a minus and then we have this expression cosine 2014 pi squared over x, and we can let that be equal to some other b because we can't like nicely express that in terms of like cosine x, cosine 2x, cosine 4x, etc. So we can write this like this 2a times a minus b, and that's equal to a minus 1. That is equal to 2a squared minus 1 minus 1, because this is equal to 2 cosine squared 2x minus 1, as we said, and cosine 2x is equal to a, so it's 2a squared minus 1, and then we subtract another one, so it becomes 2a squared minus 2. So this is equal to 2a squared minus 2, and so we have 2a times a minus b is equal to 2a squared minus 2. And so thus we see that we get a 2a squared here. Essentially, when we expand the left-hand side, we get 2a squared minus 2ab is equal to 2a squared minus 2. And so thus AB has to be equal to 1. And so that means that we basically have two cases. Either A is equal to 1 and B is equal to 1, or A is equal to -1 and B is equal to -1. That means that, so if we consider the first case, A is equal to 1 implies that cosine 2x is equal to 1. And that only happens when x is equal to some k pi, and k is some integer. And b is equal to 1 implies that cosine 2014 pi squared x is equal to 1. And that only happens when 2014 pi squared over k pi is an even multiple of pi. And then since, or I'll add another slide. And then we see that since 2014 is equal to 2 times 19 times 53, b is equal to 1 only when k is an odd divisor of 2014. So this gives us basically 3 possible values for x. And so our values for x so far are x is equal to pi, 19 pi, 53 pi, and 1007 pi. And then we have only one other case to consider, which is when a is equal to -1 and b is equal to -1 as well. And so a is equal to -1 implies that cosine 2x is equal to -1. And so then that means that x is equal to m pi over 2, and m is some odd number, and it's written like this. Okay, sorry, it was unclear. And m is odd, or we can write this as 2 does not divide m. And so then and then 2014 pi squared over m pi over 2, because b is equal to -1 as well, has to be an odd multiple of pi. And so that means that 4028 over m has to be odd. So then dividing an even number by an odd number is never going to yield like an odd number. So there's no possible values for m. And there's basically no cases when a is equal to -1 and b is equal to -1. And so the sum of all the possible values for x is just all the possible values of x that we got in our first case when a is equal to 1 and b is equal to 1. And so when we sum these, we get pi plus 19 pi plus 53 pi plus 1007 pi, which is 1080 pi. And so that's our final answer. Okay. So it looks like Travis got it. If so in the chat, quickly tell me, are there any other homework problems you want me to cover, or can I start with the number 3 for today? Um, like if most of you guys can respond, so I know like either I can move on or there's some other problem. Okay. Okay, cool. Okay, so we're gonna be doing number 3 today. Um, First, there's just some preliminaries that ideally you guys know. If any of you guys don't know any of this stuff, then like go ahead and tell me in the chat. Um, these two things I like you might know, but I don't expect you to know. But if you don't know any of this stuff, just go ahead and let me know in the chat. Otherwise, say like just put a thumbs up or say like okay or something like that. Okay. So yeah, like these are just basic like divisibility rules, like how you test if something is divisible by something else, like how you test if a number is divisible by 7 or 5 or 4, etc. And this is just noting that like if you have some some composite number, you can divide it into relatively prime numbers whose product is that number itself, and then you can test for divisibility by each of those factors essentially, and if it satisfies divisibility by each of those factors and is divisible by the original number itself. So for instance, 60, we can test for divisibility by 3, 4, and 5. Um, and then obviously like there's some basic results with respect to like divisors and multiples. Like if A divides B and B divides C, then that means that A divides C and such things like that. Which I kind of expect you guys to know. There's some basic stuff about LCM, GCD, relatively prime numbers. Basically, we should just know what those are, which I expect most of you do. Another important thing that I expect you guys know is that the LCM of, let's say, A and B times the GCD of A and B is equal to the product of A and B. If you kind of forgot about that, that's fine. This is just a refresher. And then modular arithmetic. I expect you guys to know the basics of that. So while multiplication, addition, and subtraction do follow the basic rules of modular arithmetic, division and exponentiation do not. Meaning that like obviously if you have like A is congruent to B mod M and C is congruent to D mod M, you can say AC is congruent to BD mod M. You can also say that A plus C is congruent to B plus D mod M. You can also say that A minus C is congruent to B minus D mod M. Demonstrating how multiplication, addition, and subtraction do follow the basic rules of modular arithmetic. But this should be a recap, and if it's not, then I suggest you look into modular arithmetic on your own time. I'll be covering some more advanced stuff. But these division and exponentiation work like this. So if A, B, and C are positive integers such that C divides A and C divides B, if A is congruent to B mod N and the GCD of C and N is 1, meaning they're relatively prime, then A over C is congruent to B over C mod N. And for exponentiation, if A is congruent to B mod N, then A to the K is congruent to B to the K mod N for any positive integer K. And for exponentiation, you can note that obviously like if you're like somewhat strong in like factorizations and expansions and algebra and such, then like the proof is quite simplistic. You can note that by saying that A is congruent to B mod N, you can deduce that N divides A minus B, and A minus B divides A to the K minus B to the K. And so thus we can deduce that N divides A to the K minus B to the K, which implies that A to the K is congruent to B to the K mod N. And like A minus B always divides A to the K minus B to the K. Because we can always write it we can always write A to the K minus B to the K as A minus B times some other expansion. Okay. So then next what I'd like to cover is some strengthened divisibility rules essentially. So first there's a strengthened divisibility rule for 3 and 9 which basically like so if you have some number mod if you take some number mod 3 or mod 9 then you're essentially gonna get its remainder. So what I'm saying is that if you let M be the sum of digits of some positive integer N, then N is congruent to M mod 9. Basically what this is saying is that if you have some positive integer N and you take it mod 9, then that's congruent to its remainder mod 9. So if I have some like random 4-digit number or something, I can just take it I can basically just say that the original number N should be congruent to its remainder modulo 9 because more rigorously you can write any number N as dk minus 1, so on, d2, d1, d0. And then when you expand that, you can write it in terms of like base 10, so 10 to the k times dk, 10 to the k minus plus 10 to the k minus 1, dk minus 1, plus so on, plus 10 squared times d sub 2, plus 10 to the 1 times d sub 1, plus 10 to the 0 times d sub 0. And then what this shows you is that in fact this number N, if you take it mod 9, then you're just gonna get 1 to the k times d sub k plus 1 to the k minus 1 times d sub k minus 1 plus so on. And you'll get like your last few terms will be this. Which is congruent to essentially the sum of the digits. And that's congruent to M mod 9. So what this shows is that like any positive integer is congruent to the sum of its digits mod 9. And like why this is useful is that like sometimes in problems you can't exactly find the sum of the digits or anything like that, but you can like if they give you some random arbitrary number, they're like, oh, there's some number N, but they don't give you what exactly that number is. You can't actually find the sum of the digits or anything like that, but you can say that the number itself is congruent to the sum of its digits mod 9. So this is just a general like congruence that you can use whether you know the exact specifics of the number or not. And then another thing is there's a strengthened divisibility rule for powers of 2 or 5. So what this is that for non-negative integers N, A, and B, the remainder when N is divided by 2 to the A times 5 to the B is the remainder when the last max A comma B digits of N is divided by 2 to the A times 5 to the B. Meaning like if you're dividing by like 2 to the square 2 squared times 5 to the 3, then if you just take the last 3 digits, because 3 is a larger exponent, then you can just divide those last 3 digits by 2 to the a times 5 to the b, and that will give you the same remainder. And then again, the proof is fairly straightforward. You can use something similar to this. And yeah, and you're essentially just proving that like you can just you can essentially just write it like ultimately you're gonna have like 10 to the max AB times d max AB. And what you should end up proving is that you're gonna get 10 to the 0 times when you take it mod 2 to the a times 5 to the b, it's gonna become basically the first 3 terms, and then everything else after, and then basically every term from 10 to the max AB minus 1 times D max A comma B minus 1. Every term after this will be 0. So you'll get 0 times D max A comma B plus 0 and so on. Mod 2 to the A, 5 to the B. So you can write it in this kind of like canonical representation. You can write it as like 10 to the something times each of the digits, and then you can just take it mod 2 to the a times 5 to the b, and you want to like keep track of the terms that surround the term 10 to the max of a and b times d sub max a and a comma b. But essentially all this is that you can take the max of a and b, and then if you take those many digits at the end, then you can just find the remainder when those digits are divided by 2 to the a times 5 to the b. So this is a pretty simple example problem. So I'm just gonna go through it real fast. It's a 79-digit number. You write the integers from 1 to 44 in order one after the other, and then you want to find the remainder when n is divided by 45. All you have to do for this problem is note that 45 is equal to 9 times 5, and 9 and 5 are relatively prime. So you can just check for divisibility by 9 and 5. And like the remainders when it's divided by 9 and 5. So first of all, you can note that this n is congruent to 4 mod 5 because the last digit is just 4. And then after that, you can note that if you like n should be congruent to the sum of its digits m, or rather to make things easier to understand, s mod 9. N is congruent to the sum of its digits s mod 9. And then the sum of its digits would be 1 plus 2 plus 3 plus so on till 44. And that's equal to 44 times 44 plus 1, or 45 over 2. And that gives you 22 times 45, which would give you 990. And that's congruent to 0 mod 9. Thus, n is congruent to 0 mod 9. And so then you see that n is divisible by 9 and it's 4 mod 5. So if it's 4 mod 5, then that eliminates A as an answer choice. And that also eliminates, that should also eliminate D as an answer choice. And then if n is congruent to 0 mod 9, that means it's divisible by 9, so that eliminates this as an answer choice and this as an answer choice. And so the only possible answer is really C. Because it has to be both congruent to 4 mod 9 and 0 mod 9, and C or 9 is the only answer choice that satisfies this. This is a pretty simple AMC problem. And then I'm gonna walk you through modular inverses. So this lesson is pretty like theory heavy. Because you're like, if you're good with the theory in number theory, then like or like the concepts, then you should be able to apply it pretty easily to complex problems. So modular inverses in normal arithmetic, you can say that a times the inverse of a is equal to 1, and you can do something similar in modular arithmetic. So in modular arithmetic, we can define the modular inverse to be the number mod n such that a times the inverse of a is congruent to 1 mod n. And you can say that a to the -1 is the inverse of a mod n. And the modular inverse is defined if and only if the GCD of A and N is equal to 1. And if you don't believe that this modular inverse exists, what you can do is that, first of all, you can prove that the residues formed by AK for all 0 less than or equal to K is less than N are unique mod N. And then the way you can do this to prove that all the residues are unique is that you can set up a proof by contradiction. And you can say that, for instance, A times some K is congruent to A times some J mod N, but K is not congruent to J mod N. And then using the definition of modular arithmetic, that means that N has to divide A times K minus J. And since the GCD of A and N is equal to 1, this implies that N divides K minus J, but K and J are not congruent mod N. So, and they're both between 0 and N, 0 inclusive and exclusive. So their difference cannot be divisible by N no matter what. And so there's a contradiction basically, provided our initial assumptions. And so we achieve a contradiction. And so the modular inverse exists, essentially. Okay, and then there's some basic operations, for modular inverses. So you can add and multiply modular inverses, and then obviously subtraction works the same way as addition, except it's just negative, and multiplying works the same way as division. So for adding inverses, if you have some integers a and b, they're relatively prime to n, then you have that the sum of their inverses is congruent to a plus b times the inverse of ab mod n. And the proof is that a plus b times ab, the inverse of ab, is equal to a times a inverse times b inverse plus b times a inverse times b inverse, which is congruent to b inverse plus a inverse mod n. And for multiplying inverses, for integers a and b that are also, again, relatively prime to n, a inverse b inverse is congruent to ab inverse mod n. And the proof for this is you can note that ab, the inverse of ab times ab is congruent to 1 mod n. And a inverse times b inverse times ab is also congruent to 1 mod n, and it's actually congruent to a times a inverse times b inverse, which is congruent to 1 mod n. And so hence proof. For negative exponents, we can define any negative exponent mod some n. And so m to the power of negative a is the inverse of m to the a. And we can also write that as m to the negative 1 times n to the a. And both definitions should give us the same residue. So here's another question. You can read it and then try it for like maybe a minute or two. Okay, so I'm gonna start explaining this. So we can first let A be the average of first 6 tests. So then we know that 6A plus 95 is congruent to 0 mod 7, or is a multiple of 7. And this means that 6A is congruent to negative 95 mod 7. And we can add 98 to both. We can basically if you have that something is congruent to something mod 7, you can add any multiple of 7 to this to make it a positive integer. And it's the same thing like modulo 7. So negative 95 mod 7 is the same thing as negative 95 plus 98 mod 7, since 98 is a multiple of 7, so it's just congruent to 0 mod 7, so we're basically adding 0, which is congruent to 3 mod 7. So 6A is congruent to 3 mod 7, meaning that A is congruent to 3 over 6 mod 7, or 1/2 mod 7, which is 1 mod 7 is the same as 8 mod 7, so we can write this as 8 over 2 mod 7, which is 4 mod 7. Thus, A is congruent to 4 mod 7. However, A has to be from 91 to 100. Thus, the only possible value of A, since A is congruent to 4 mod 7, is 95. And so then if we let the 6 score be some S, and the average of the first 5 tests is B, then 570 is equal to S plus 5B. And we see thus that 570 is a multiple of 5, 5B is a multiple of 5, thus S has to be a multiple of 5. So 5 divides S. And so thus, because again, S is between 91 and 100, and the answer choices are 92, 94, 96, 98, and 100, then the only possible answer for this question is 100. The only possible value of S is 100, because only one of the answer choices is divisible by 5. Okay. Are you guys good with this question? Do you have any questions, or can I move on? Just text in the chat real quick. Okay. So the answer to this question is 100. And then now I'll quickly cover Wilson's theorem and its proof. So Wilson's theorem states it doesn't appear like a whole lot in AMC and AIME, but it does appear sometimes. So Wilson's theorem states that for any prime p, p minus 1 factorial is congruent to negative 1 mod p. And the proof is that you can notice that the numbers 2, 3, 4, so on till p minus 2 all have modular inverses, unique modular inverses. And so modular inverses come in pairs. The only exception is 1 and itself, and negative 1 and itself, essentially, because they're it's their own modular inverses essentially. But there are every other like all the rest of the residues mod some m in general, not necessarily a prime number, have modular inverses that come in pairs. So the numbers from 2 to p minus 2 have modular inverses that come in pairs, and then 1 and p minus 1 are obviously exceptions. So if you compare, like, for instance, each of these numbers, like, you can basically form so there's p minus 3 numbers from 2 to p minus 2, and you can basically form p minus 3 over 2 pairs of numbers such that the product of the numbers in each of the pairs is 1 mod p. Because we can basically just pair the modular inverses, and the product of each of those numbers in those pairs should be 1 mod p, right? So when you multiply all of them, you get 1 mod p again. So it's like we have like a times A inverse times B inverse times C inverse, so on. And this is like, you can form all of this from just the numbers, the residues from 2 to p minus 2. And then you have two residues left, 1 and p minus 1, that you can't pair up to get a product of 1 mod p. And so this thing is 1 mod p. And so like the only thing you have left is just this p minus 1. So the actual product of p minus 1 factorial should just be congruent to p minus 1 mod p. And that's just congruent to negative 1 mod p. So this is a question that utilizes Wilson's theorem that you can go ahead and try for like a few minutes. Okay. So you want to compute the smallest positive integer n, such that 9 times n plus 3 divides 4n factorial plus n plus 5. So brute force can work here, but there's an easier route. So if you actually try numbers to begin with, you're gonna notice that the numbers from 1 to 5 do not work. What this means is that n is at least 6. So that means that 4n factorial is divisible by 9, because like 6 factorial has a 6 and then a 3. So then this is divisible by 9. So that means that and then you're just multiplying it by 4, which doesn't really do anything. So 4n factorial is divisible by 9. So 4n factorial plus n plus 5 is just congruent to n plus 5 mod 9. And so then from here we can see that n has to be congruent to 4 mod 9, because we see that we want 9 times n plus 3 to divide this expression. And this expression is just congruent to n plus, and then this is divisible by 9, which means that 9 has to divide this, and then this is always divisible by 9, which means this has to be divisible by 9. And so we want this to be congruent to 0 mod 9, which means that n has to be congruent to 4 mod 9. So we want n to be congruent to 4 mod 9. Then you can suppose that, so we have that if n is congruent to 4 mod 9, then 9 divides this, but we also need n plus 3 to divide this. So you can consider the case when n plus 3 is a composite number. And in that case, since n is greater than or equal to 6, we have that 2n is greater than n plus 3. And so thus, n factorial necessarily has to be a multiple of n plus 3. Or n plus 3 divides n factorial is like the notation you can use. And thus, you would need n plus 5 to be a multiple of n plus 3. Since n plus 3 divides this part, and so thus n plus 3 has to divide n plus 5. But that's not possible because they just differ by 2. And so thus n plus 3 has to be a prime. And so then the smallest possible n that would satisfy the above conditions that we outlined would just be 40. And the reason being that we have that n is congruent to 4 mod 9, and we have that n plus 3 is prime. So there really aren't many options. You can list out the values of n that satisfy this. And if you do that, you would get 4, 13, 22, 31, 40, 49, 58, etc. And you want n plus 3 to be prime, so this would give you 7. Um, however, we have that n is greater than or equal to 6, so this doesn't work. And then this would give you 16, which is not prime. This would give you 25, which is not prime. This would give you 34, which is also not prime. And this would give you 43, which is prime. So 40 is our smallest possible number, as I said. And so thus 40 would be the answer for n, the smallest positive integer n. And the way Wilson's theorem kind of comes into play in this is if you want to check your answer, you can note that 40 factorial is congruent to -1 over 41 times 42 mod 43. And that's just congruent to -1 over 2 mod 43. And if you compute 4 factorial, if you compute the original expression, then which is 4 factorial plus n plus 5, and then you would get 4 times -1/2 plus 40 plus 5 mod 43 is equal to 40 plus 5 minus 2 is equal to 43. So mod 43 is just 0 mod 43. So using Wilson's theorem, you can check that indeed it satisfies the conditions of the problem. So let me know in the chat if you're good to move on, or if you have any questions. Okay. So next is the Chinese remainder theorem. There's two main archetypes for the Chinese remainder theorem. Either you can stitch together congruences, you can take them apart. So like as I discussed earlier, it's like if you have a bunch of like relatively prime mods, so you have like mod A1, mod A2, mod A3, so on, mod AK. And these AIs are all relatively prime. Then you can get some sort of congruence in terms of mod A1, A2, so on, AK, or the product, essentially mod the product of AIs. And you can also take apart congruences. That's another part of the Chinese remainder theorem. So if you have like mod some product, then you can split it into a bunch of mods of relatively prime numbers like this. So if you have mod 1000, for instance, you can split it into mod 6, mod 8 and mod 125. So that's a brief overview of the Chinese remainder theorem. And then we're gonna skip this question for the time being, and if we have time, we'll come back to it. This is a question that you can try to give a go. So, because we're kind of we have a time limit for this class, I'm gonna start explaining. So first of all, this first condition states that n is a multiple of 16, 15, and 14. So this means that because it's a multiple of each of these numbers, this makes it a multiple of every positive integer under 14, except for 9, 11, and 13. And that forces a value of x, y, and z then, because these are the only possible values such that the remainder is not 0 when you divide by it. So then we can because n is a multiple of 16, 15, and 14, we can let it be some number times the LCM of 16, 15, and 14. And the LCM of these numbers is 1,680. So we can write as 1,680n. And then we can solve, we know that it leaves a remainder of 3 when it's divided by x, y, and z, and these are the only possible values of x, y, and z. So we can write 1,680n is congruent to 3 mod 9. 1,680n is congruent to 3 mod 11. And 1,680n is congruent to 3 mod 13. Then we see that so if we divide 1,680 by 9, then we would get it would give us negative, basically this is congruent to negative 3 mod 9, and so you get negative 3n is congruent to 3 mod 9, and so then n would be congruent to negative 1 mod 9. Yeah, except you would get n is congruent to negative 1 mod 3, because as I discussed when you do division and modular arithmetic, if I'm dividing by negative 3 on both sides, I'd have to divide 9 by the GCD of negative 3 and 9, which is 3. It was, if A is congruent to B mod M, then A over C is congruent to B over C mod M over the GCD of M and C. So the GCD of 9 and negative 3 is 3. So you get n is congruent to 1 or negative 1 mod 3. And so then n is congruent to 2 mod 3. And then similarly, you can solve each of these two congruences and you would get n is congruent to 10 mod 11 if you solve it, and n is congruent to 1 mod 13. And then from there, it's easy to deduce that n is 1 less than a multiple of 3 times 11 or 33. So that means that n can be written as negative 1 mod 33. And thus n can be parametrized as 33k minus 1. And then plugging this into our other congruence, we have this is congruent to 1 mod 13, which means that 33k is congruent to 2 mod 13, which means that 7k is congruent to 2 mod 13, and we did that because 33 is 2 times 13 plus 7. So 33 is congruent to 7 mod 13. So you get 7k is congruent to 2 mod 13. And then what you can do is that means 7k is congruent to 28 mod 13, and I got that by adding 2 times 13 or 26 to 2. So 28 is congruent to 2 mod 13. And we can divide by 7 on both sides now, and k is congruent to 4 mod 13. So that means the smallest possible value of n is just 4. And that would mean that n is 4 times 33 minus 1, which is 132 minus 1, which is 131. And n is equal to 1,680 times 131, that means. And you want to find the sum of the distinct prime divisors. So that would just give you 131 plus 2 plus 3 plus 5 plus 7. 2, 3, 5, and 7 divide this 1,680, and 131 is prime. So this would give you your final answer of 148. So text in the chat if you have any questions for this problem, or if I can move on to the next one. Okay. So now I have some problems on splitting congruences. Um for these problems, a kind of preliminary that you guys should know is Fermat's little theorem, which states that if you have a prime p, then for any integer a, we have that a to the p is congruent to a mod p. And an alternative way to write this is that if you have some prime p, if a and p are relatively prime, then a to the p minus 1 is congruent to 1 mod p, and we just got this by dividing by a on both sides. But this here would be mod p over the GCD of a and p, and so it'd only be p if this value is 1, meaning if the GCD of a and p is 1 or a and p are relatively prime, then we can say that a to the p minus 1 is congruent to 1 mod p. So this is always true, and this is always true as long as a and p are relatively prime. And so this is a problem that utilizes Fermat's little theorem. So you can go ahead and try it for like 1 or 2 minutes, and then I'll go over it. Um, no, it's not 62, but I'll go over the solution now. So by the Chinese remainder theorem, so we can basically just first of all note that n squared is congruent to n mod 16, and n squared is congruent to n mod 625. This is because n squared is congruent to n mod 10,000, and then we can split it into 16 and 625. And so then this implies that n times n minus 1 is congruent to 0 mod 16, and n times n minus 1 is congruent to 0 mod 625. And so we can first just ignore the restriction that a cannot be equal to 0, and we can just say that obviously n is either 0 or 1 mod 16, and n is either congruent to 0 or 1 mod 625. And that gives us 4 cases. So all you have to do basically is check those 4 cases. So if n is congruent to 0 mod 16 and 625, that means that n is just congruent to 0 mod 10,000. And that gives us that that means that a is equal to 0, which is what we don't want. And if n is congruent to 1 mod 16 and 625, then that gives us a is equal to 0 as well, because we get 0, 0, 0, 1. R. Yeah. And so this also gives us a is equal to 0, and we don't want this case as well. And so because this would give us that n is congruent to 1 mod 10,000. And so then we just have two possibilities left. Either n is congruent to 0 mod 16 and 1 mod 625, or 1 mod 16 and 0 mod 625. And if you check these two and find the solutions, then what you can do is, if we consider this first one, then this would mean n is equal to 625 n plus 1. And that means 625 n plus 1 is congruent to 0 mod 16, using our first congruence. And that means, and we can note that 625 is equal to is congruent to negative 15 mod 16, because 640 is congruent to 0 mod 16, and 625 is 15 less than that. So we get n plus 1 essentially is congruent to 0 mod 16, which means that n is congruent to 15 mod 16. And this one right here gives us, that means n is equal to like some 625 times some lowercase n. And then we can see 625n is congruent to 1 mod 16. And so that means n is congruent to 1 mod 16. So if n is equal to 1, then n is equal to 625. So the last four digits would be 0625, and a is still 0, which is what we don't want. However, and if we use the first case, in which case we got the n is equal to 15, because we got n is congruent to 15 mod 16, then we would get 625 times 15 plus 1, and that gives you 9,376. And that would end up giving you a is equal to 9, which is not equal to 0. And so you would end up getting that n is congruent to 9,376 mod 10,000. If you check, you would get that it's congruent to this mod both 16 and 625. And so thus it's congruent to 9,376 mod 10,000, thus a is 9. And so BCD, ABC, the first three digits of what you get when you take mod 10,000 would just be 937. Because asking for ABC, which is these first three digits. So we just divided this into two congruences and then split that up into four cases. Two of the cases we ruled out immediately, and then we verified which of the remaining two cases actually works, is what we did for this problem. So text in the chat if you have any questions, or if I can move on. Okay. So I'm gonna skip this question for now so I can get through the rest of the stuff. The questions I don't get to will be for homework, and I'll assign some more questions for homework as well. And just do as many of the problems for homework as you possibly can. I know that like you guys don't have, like, some people have more time than others essentially. So this is Euler's totient function. Euler's totient function describes all the positive integers less than or equal to n that are relatively prime to n. So we define phi of n. We write this as phi, and the symbol looks like this. Phi of n is number of positive integers less than or equal to n that are also relative prime to n. And it so the phi function, there's some properties about it. So first of all, it's a multiplicative function. So for relatively prime m and n, phi of m times phi of n is equal to phi of m times n. The basic idea of the proof is we can just use Chinese remainder theorem to find all possible congruences. And mod m and n, but I'll leave that as an exercise that you guys can do in your own time. And how we can actually express the phi function is phi of n is equal to p1 to the e1 times p2 to the e2 times so on. Sorry, if n is equal to this, then phi of n, since it's the number of like positive integers that are relatively prime to n that are less than or equal to n, then it's kind of like complementary counting that we can use here. So it's like you have n positive integers, and then for the prime p1, let's say 1 over p1 of the numbers from 1 to n are like divisible by p1. Then let's say approximately 1 over p2th of the numbers from 1 to n are divisible by p2, and so on. So then you can multiply by 1 minus 1 over p1 times 1 minus 1 over p2 and so on times 1 minus 1 over pk. And you can also write this as p1 minus 1 over p1 times p2 minus 1 over p2 times so on till pk minus 1 over pk. So this is like the formula for phi n. And then you have and then there's this theorem called Euler's-Toshin theorem, and that states that for relatively prime a and n, a to the phi of n is congruent to 1 mod n. And this is actually a generalization of Fermat's theorem, which states that a to the p is congruent to 1 mod p that I covered earlier. And like, so if n is a prime, then phi of p is just equal to p minus 1. And so that's how you get a to the p minus 1 is congruent to 1 mod p. So yeah. So that's a brief introduction to the Toshin function, but obviously like there's more that you can learn. Like I'd suggest you to search up or learn about it more. But you don't need to know much about it. It's more about like using it in questions and understanding what it is. And then Diophantine equations are just equations that can be solved over the integers essentially. There are different ways to solve Diophantine equations in computational contests such as AMC and AIME. Usually you can use Simon's favorite factoring trick, which just states for x, y, a, b, all integers, are usually integers, not necessarily integers, x, y plus ax plus by plus ab is equal to x plus b times y plus a. You just want to be able to rearrange the terms and equations so that one side can be written as something plus something in parentheses times another something plus something. So something of this form. And then there's some other like typical Diophantine equations that have like common parametrizations that I can cover. So for instance, let's say x and y are positive integers. And n is equal to p1 to the e1 times p2 to the e2 and so on pk to the ek. And that is its prime factorization. And suppose you have some Diophantine equation, 1 over x plus 1 over y is equal to 1 over n. You need to solve this over integers, as you do for any Diophantine equation. Then the number of solutions to this is just the number of factors of n squared, and that's what this symbol means. And that is just equal to 2e1 plus 1 times 2e2 plus 2, 2e2 plus 1, and so on, times 2ek plus 1. The reason being that you can just use Simon's favorite factoring trick here. So you can multiply both sides of the equation by nxy, and that would give you nx plus ny is equal to xy. And so then taking the nx and the ny to the right-hand side of the equation, you can you would get xy minus nx minus ny is equal to 0. So you can add n squared to both sides of the equation, and you can factor the left-hand side, and you get x minus n times y minus n is equal to n squared. And so obviously you can see that the number of possible values for x, like once you determine x minus n, then y minus n is fixed. And so the number of possible values of x minus n is the number of positive integers of n squared, which is this, as we said. Also for Diophantine equations, I'd like to note that like knowing key factorizations is important. A common one that like you don't learn in school, or like that people forget, that is still important to know, actually very important, is that x cubed plus y cubed plus z cubed minus 3xyz is equal to x plus y plus z times x squared plus y squared plus z squared minus x y minus yz minus cx. And another thing is that if you have a linear equation with two unknowns, that's a quadratic, that's a Diophantine equation. So like ax plus by is equal to c. Then it has integer solutions if and only if the GCD of a and b divides c. If the GCD of a and b is equal to 1, and x sub 0 and y sub 0 is one integer solution, then the general solution can be written as x is equal to x0 plus bt and y is equal to y0 minus at, where t is an integer. T is some integer. So for instance, a very simple example is if we have 19x plus 7y is equal to 260, then we can immediately see that one solution is x is equal to y is equal to 10, because that gives us, this is 190, this is 70, and then when you sum them, you get 260. Now we can apply the method listed above to find the general solution. So x in general would be equal to 10 plus 70, and y in general would be 10 minus 19t. And then you can see that you want, if t is 1, then this is negative. If t is greater than or equal to 1, basically this is negative. So you want t to be less than or equal to 0 from here, and then you want 10 plus 7t to be positive as well, because it asks for, so we're trying to find positive integer solutions to the equation 19x plus 7y is equal to 260. So we want positive integer solutions. From here, we need that t is less than or equal to 0. From here, we need that 7t is greater than negative 10, and that gives us t is greater than negative 10 over 7. So t is greater than, t basically has to be greater than or equal to negative 1. And so t is less than or equal to 0 and greater than or equal to negative 1. If t is 0, then we just get this initial solution. If t is negative 1, then that gives us x is 3 and y is 29. And so the only two positive integer solutions are 10, 10 and 3, 29. And that's it. So that's linear Diophantine equations. But there's other like possible types of Diophantine equations, or like other parametrizations rather. So you can have a quadratic equation with 3 unknowns as a Diophantine equation. So if you have something like x squared plus y squared is equal to z squared, which kind of looks like the Pythagorean identity, then all positive integer solutions x comma y comma z that satisfy that the GCD of like all three is equal to 1 can be parametrized as x is equal to a squared minus b squared, y is equal to 2ab, and z is equal to a squared plus b squared, where integers a is greater a and b are both integers, a is greater than b, and one of these is even, and one of them is odd, and the GCD of a and b is equal to 1, so they're relatively prime. This is a parameterization of Pythagorean triples, but it is like it can show up as a Diophantine equation. And like for most Diophantine equations, parameterization is a very important technique that you should keep in mind. And then the other possibilities, you have a quadratic equation with 4 unknowns. So for instance, you have like the equation x y is equal to zt. The way you want to tackle this is you want to if you see this in a problem, you can let x over z. So x over z is equal to t over y, just rearranging the equation. You can let that be some constant m over n. And so then thus you would have that if the GCD of m and n is equal to 1, x is equal to pm, z is equal to pn, and then t is equal to qm, and y is equal to qn. And this holds where p is equal to the GCD of x and z, and q is equal to y over n. And so you can just basically parameterize your variables x, z, y, and t like this. And it will seem kind of abstract, so I'll show an example of how to use this as well. But first, I have this question right here, which you can go ahead and try to solve for like 1 or 2 minutes. Alright, so we're almost out of time, so I'm gonna cover the solution. We can basically expand some stuff. We get x squared y squared plus x squared plus y squared plus 1 plus 2x minus y times 1 minus xy is equal to 4 plus 4xy. And x squared y squared plus x squared plus y squared plus 1 plus 2 times x minus y times 1 minus xy is equal to 4 plus 4xy. And then we can take the 4xy to the left-hand side and distribute it into two xy's, and we would get x squared y squared minus 2xy plus 1 plus x squared plus y squared minus 2xy minus 2 times x minus y times xy minus 1 is equal to 4. And so then we can write that as xy minus 1 squared plus x minus 1 of x minus y squared from here minus 2 times x minus y times xy minus 1 is equal to 4. And then you see that this is again like something squared plus something squared minus 2 times like their product. So it becomes xy minus 1 minus x minus y squared is equal to 4. And that implies that xy minus 1 minus x minus y is equal to 2 or negative 2. And this left-hand side can be written as x plus 1 times y minus 1, and that is 2 or negative 2. So that gives us, so using that factorization, that would give us the solutions negative 3 comma 2, negative 2 comma 3, 0 comma negative 1, and 1 comma 0 as our solutions. So let me know if you have any questions for this problem. And I'll cover like one last problem that utilizes the parametrization I discussed for quadratic equations in 4 variables. Um, so I'm gonna cover this problem as the last one, and the remaining you can try as homework, and I'll give you some more homework problems too. But from what I discussed, given this, we can write it as A over C is equal to D over B is equal to M over N. And then you can write A as PM, C as PN, D as QM, and B as QN. And now you can plug these numbers in, and you get the A to the fourth plus B to the fourth plus C to the fourth plus D to the fourth is equal to P to the fourth M to the fourth plus Q to the fourth N to the fourth plus P to the fourth N to the fourth plus Q to the fourth M to the fourth. And just plugging these parameterizations in to this, and that gives you this, and you can factorize this as P to the fourth plus Q to the fourth times N to the fourth plus N to the fourth. And note that P, Q, M, and N are all positive integers, so this has to be at least 2, and this has to be at least 2, meaning that this product cannot possibly be prime. It has to be a composite number. So thus, like, it cannot be prime. That it's hence proof. Because each of these factors are greater than or equal to 2. So that's how we can use a parametrization like this in problems. I did not get to go to bases. So I suggest you try these numbers by yourself, these problems by yourself, and then maybe read on chicken McNugget theorem yourself, and I can briefly cover it at the beginning of next class as well, or I can record a video covering that section and post it and send it as an email. But let me know if you have any questions for the last 2 problems, and any questions in general, you can stay back. But otherwise, that's the end of the number theory lesson, and I'll be assigning homework. And I'll send a solution video most likely for the rest of the algebra problems, and I'll send, yeah, and I'll do the same for the rest of the lessons as well.